Okay. Yeah. So now we reach one of the the topics that are remaining. One of the sort of last things that we will cover in this course, but it's a very crucial topic nonetheless. That is Gaussian beams. So if you remember, I mean the setup that we have, which we are sort of following in order to unfold this course, that of trapping a microparticle or nanoparticle inside a fluid. So different components of that we have been studying. This is one of the last things that we are going to study, and that is, however, very crucial. And the reason that it is crucial is that, see, so we have, of course, a laser beam, and all laser beams have a Gaussian as the transverse intensity distribution. Transverse intensity means the intensity distribution perpendicular to the direction of propagation. And this is like a Gaussian beam, as you know, and the way the beam evolves is different in the Z direction and in the XY direction. That is very important in the context of optical trapping because of two reasons. One is, of course, that the beam size, which is of immense importance in trapping, is determined by the Gaussian properties of the beam. You know that, okay, so let me share the screen and just go once to that slide of mine. Yeah, so can you see? I hope you can see. So let me just open. Yeah, so here it is. So this is a very crucial part of the, yeah. So basically, when we are, so this is how the laser beam sort of it is the laser beam propagates in this manner. So there are two lasers actually. So this is one and this is one. So one is typically used for detection and this one is for trapping. So actually this is the beam that is the trapping beam really, but it doesn't matter. You can interchange the positions and doesn't matter. But what is extremely crucial, what I actually wrote here is that I think, yeah, light beams. This is where we are. So resonator optics. So of these, if you look at all these things, we have covered all of them. This light force and dipole we have not. But this is very crucial. The role of laser intensity. This is extremely important in the sense that, I mean, this lens that you have, this objective lens that you have, microscope objective lens, it has a very high numerical aperture, which means that the spot size inside this is extremely small. So how you quantify that spot size is something that is so unless you know what kind of beam sizes you will get, what is when you focus a beam by a lens, what is the beam spot size? So beam spot size basically gives you the intensity. It's an intensity, is power by area. Very simply, I mean, in experiments, that's how we measure intensity. So if the spot size is, unless the spot size is very small, you will not get very large intensity. So therefore, it is absolutely crucial to understand how a Gaussian beam evolves spatially, and that is what we are going to study now. Okay, how it sort of so what are the parameters? There are some beam parameters, as they say. So those beam parameters control how the Gaussian beam is going to change spatially, and that is again, as I said, that determines the trapping force, because the intensity, the larger the intensity, the larger is the trap force. That is something which again we will cover in this course for sure. There is I think there's a group who is presenting it in the seminar, so that we may, yeah, we can do that, or if we have time we can probably go over a little bit ourselves as well in the part of the course as well. Okay, so this is how. And also what is important to remember is that at the end we will study this resonator optics, where indeed so we just studied what we finished just now was the ABCD matrix, matrix, the way we understand how a light ray interacts with with an optical element, and that is by the use of these ABCD matrices. And each of these mirrors and lenses have a unique ABCD matrix. So, however, our treatment was considering light as rays. That is not correct, because at the end, actually, you have light beams going on. So, what we will study today, starting from today, is essentially light beams, and the simplest light beam is the Gaussian beam. The beam whose transverse intensity distribution looks like a Gaussian. And what we will basically understand later on is in terms of designing resonators also, we have to consider not rays, because that is not the true picture, but actual Gaussian beams. So and how they interact with these different optical elements, and especially what is the treatment in terms of of designing optical resonators or optical cavities. What is that we have got to look for? Okay, so that is extremely important, and that is what we will study. So at the end, after this, what we just have is a bit of diffraction theory, which basically takes us to kind of or mostly the elements that I covered last year, and I think we are well in time. Probably we should finish before the end of the month, at least the part that I typically cover in this course, which is which is good news. Okay, so let us start.
Sir, if we have to use the Gaussian beam optics, why
Uh,
did we study that ray picture ABCD matrix if it is not
So
correct?
basically, the starting is much easier to deal with rays. So remember, when I typically look at how mirrors or lenses work, the ray picture suffices. Okay, it's only when you come to a cavity, a resonator, there it is crucial that you consider a Gaussian beam, the resonator. But when you are designing, say, optical, a car headlight or something, you don't need to consider a beam. And that, I can tell you, Rohan, is a very, very significantly important, industry. Designing, the ray optics picture is very crucial, very important. And for
Okay.
that, the beam does not, you don't need the beam. And it's always better to consider that it's a much more simpler thing than the Gaussian. In fact, the Gaussian treatment is essentially useful for designing cavities, not just for looking at how these light interacts with mirrors and lenses. It's only when it sort of folds on itself, then this Gaussian treatment is crucial. Okay, so let us actually, this is I should not name this as Gaussian, not maybe. Okay, I think it's important to write as light beams, because remember that, oh, fantastic, the Gaussian is the Gaussian that we know is the simplest of all beams. So that is just a class of beams. These are all called Gaussian beams, in the sense that the Gaussian, as you might be knowing, is the ground state or the most fundamental state of the Hermite polynomial series, and the zeroth state is what we typically call the Gaussian beam. But there are much more, so what lasers constitute have, or the beam profile of lasers is like the fundamental Gaussian beam. However, there are more exotic Gaussian beams, which that also we will just look at. That is important in the sense of these are also beams which carry angular momentum. That we might not. I think that is being covered by somebody in the this thing in our presentation. So that is nice. So let us start. So the where we ended. So the first thing, of course, I think you guys are familiar with this stuff, but we will still go over it, and that is, so we start with, so any light field, you may say, is a consequence of the paraxial equation of light. which we I think which we derived when we did the wave equation, and the paraxial wave equation is of course del square x by del t square, and this is of x y z is given by c square del square e x y z del z square. Z is the direction of propagation of light. Always, this is what we consider in optics, that z is the direction of propagation, the longitudinal direction. The transverse are the xy transverse direction. This is the longitudinal. We typically write this as longitudinal. So we have covered this to some extent before. Oh, yeah. Okay. So you know that the possible solutions, of course, are very much the plane wave solution, where we typically just have this as some e0 e to the I k z, and all that is quite fine. Uh, what is very important is that, so this is like, okay, so the plane wave solution completely satisfies this. We also have the spherical wave solution, which is of the form of something like E0 by R e to the ikz, where R is your the radius vector, which is just root of these x square plus y square plus z square. So this is a plane wave. This is a spherical wave. Both these solutions, of course, cannot describe a a beam. And why is that? Why is that? Why do these not satisfy the solutions for a beam?
So because beam has a finite transverse extent.
Yes, so this, but then this one is not really finite, right? You have normalizing by R. So this one, why is this? So this has a infinite transverse extent. Why? What about this one?
This one, this is not unidirectional.
Absolutely, very nice. So this is actually not in, this is exactly absolutely perfect what it has said. So we basically need, so a beam is unidirectional and has a finite transverse extent. That is what we need for a beam. So both of these do not qualify. So these do not qualify. Both of these do not qualify. Okay. So we are, however, looking for solutions now. So the type of solutions we are looking for is something like just some E0 of R and e to the ikz. This is very important. This, I say, is the transverse part, transverse component, and this part is my longitudinal. And remember that for a beam, it is perfectly fine if in the z direction it is like a plane wave, because a beam indeed has infinite extent in the z direction. It's in the transverse direction that there is a problem. Okay, so what is crucial in then is that the entire treatment that we're going to do now is essentially on this part, completely on this part. And what is important here is that we need to sort of find a distribution for this. But very importantly, while that distribution will depend on the transverse component, which here, so I think it's better. So this r and these are not the same. So this r is actually the radius vector which has the entire thing. Okay, x square plus this what I'm using here. This is, maybe I should just put an r dash or something. So this is just a transverse part. This is root of x square plus y square. What is important is this is still going to change with z, in the sense that at a certain z plane, this is going to be fixed, but as you change the z plane, this will actually evolve. So even here, when we finally design the solution, there needs to be some kind of a z dependence, which is what really makes this treatment somewhat complicated. Because here, of course, there is no dependence on xy. This is just a plane wave. But in this part, there is going to be a bit of z dependence, because uh, we cannot not assume. Okay, so we start with assuming that there is a z dependence, and then we find out how that z dependence looks like, because the guiding equation essentially is the paraxial wave equation. Okay, so essentially, if I take this, then the paraxial equation becomes wave equation looks like something like del square E plus k square equal to 0. What is important, however, I have tacitly, what is the meaning of this? The paraxial wave equation essentially means that the variation of E0 x, y, z is very small in the z direction, but compared to that in the x, that in the xy direction, and that straight allows us to make certain assumptions about this thing when we write in terms of this. When I have this, I actually have this. This is a spatial. This is the Laplacian, and this actually has both x, y, z coordinates, all three x, y, z coordinates. But since the the variation is much higher in the z, I mean in the xy compared to the z, you are all familiar. I mean, those are at least the fiber optics experiment, though they are quite familiar, that we can now write this chap. We can basically make this crucial assumption that lambda del E0 del Z is much, much lesser than E of Z, and lambda del square E del Z square is again much, much lesser than del E0. This, right? So that basically means that, okay, so I can just write this as k. So this is essentially like, this is del, I mean, this you can write as, so in books, the typical statement is something like this: a E0 Z and lambda, not lambda square, sorry. Lambda and del square del Z square is much, much less than k. So this lambda essentially comes because you want to get the units correct. Otherwise, the units are a problem. So this allows you obviously to make certain, the equation itself sort of will get modified, in the sense that when you actually write this del square plus k square E0 of r e to the I k z, you will, so you guys, well, you want to do, I mean, can you do this? Okay, let us do it. So yeah, I mean, so you have del E0 del Z as what, I k E0 r e to the I k z plus del E0 del z e to the I k z, and then your del square. So these I don't think I'll do these anymore. I just for this one. You guys can do it, right? So you can evaluate this, right? This is very simple. But what is important, however, is that there will be this. There will be a. So here you will have a del square del z square e to the I k z, and that we can ignore, right? So if you just add these two, what you will get. So please try these steps out. You'll essentially get something like del square. So we write this as the transverse Laplacian, which is del square e square and del square x square plus del square y square e 0 plus 2 I kappa I k del e 0 z is 0, where your delta t is this. This is called the transverse Laplacian, and this is essentially my paraxial wave equation. This is essentially something that leads to beam-like solutions. Okay, the whole, the goal now is basically to find a form for this E0 R. Okay, so then I mean it is quite clear that, so you just think of it. So I have, if you just consider a beam, so a plane wave is just like all over the place, right? There's complete infinite spread. So what I need is something like this, right? So the z will be quite fine, Ez, but I mean, sorry, not Ez, sorry, the z direction. Okay, so Ez and all we are not going to think of now, but I think I told you that it demands a z component as well the moment I constrain. But anyway, forget about that. Let us not discuss it at this moment. But if I have this as z and this as x and y, this is x and say that is y. Basically, I need something which is maybe, which is 0 at the sides, and which is, yeah, so some kind of distribution which vanishes at the edges. So this distribution actually does quite well. So a Gaussian distribution will do just fine, right? So essentially, what is a Gaussian distribution? So something like if I had, some I as some E0 square e to the minus 2r square by omega square kind distribution will do fine. Okay, so what is this omega? This omega is called typically it is the waist of the beam. This is the waist of the beam, and rather, I mean the definition, the meaning is, of course, from here it's quite clear that this is the distance at which, so omega is so basically that means the distance, the or the transverse distance. So basically the transverse distance at which I becomes I0 by E square, right? When R equals omega, this is I0 by E square. So this is the definition of waist. So 1 by E square of the maximum value is called the waist. And when we talk of Gaussian beam radius, this is the waist that we talk about. Okay. So the general solution, however, we cannot just assume that this is going to be a Gaussian. So we have to write in terms of some kind of, some variables. Those variables are something that we need to evaluate. I mean, what their dependencies are is basically what we will evaluate.
Sir, when you defined waist, did you use transverse distance or lateral distance?
Transverse. It's always the beam spot, no? Beam spot size. So
Along
remember, it is, so
along
basically
Z.
my beam is going like that. The thing is here, right? So the Gaussian distribution is always like this, and this is my waist.
Oh, okay.
Okay, this is always the waist. It is always, so beam spot. Remember, when we measure beam size, basically you have a beam like that. you just insert a card, right? Like this, and then you get a shape like that, right? So this is the beam size essentially. If you take the transverse distribution, if you just say put this on image J and draw a line like that, you will get something like this, right? And the waist is essentially something like that.
Okay.
This is what we call as waist radius. The radius, very crucial, it is a radius. The radius is what I wrote, not the diameter. It's the waist radius. Okay.
Fine, sir.
Okay. So now the solution we can assume is, so we assume solutions of the form. So you see, we are kind of getting so I see the treatment that I find in Miloni, and I think most books, is that it is kind of, you're sort of assuming that there is going to be a Gaussian like nature. Okay, that is kind of there. However, you are there are some phase factors, you can say, or some factors, some dependencies on the Z, which you do not know and which you will not sort of not keep. Okay, so what I'm trying to say is that you know that this works well, so you're essentially going to write this E0 of R. Remember, I'm now dealing only with that E0, the on envelope, not the total solution, just the E0. Okay, so I'm basically going to write this as, because in the Z it's a plane wave, e to the ikz. So essentially I'm going to write this as some A0 e to the I k x square plus y square to q of z basically. Just give me a second. This is correct. If I do 1 minute, just give me. I think I once clarify this. Yeah, I think it's fine. So I'm saying that this is e to the I some pz. So I'm putting some two phase factors, q and p, which have z dependencies. Okay, I'm trying to find out what those dependencies are. Okay, that is, so I know that my guiding equation is the paraxial wave equation that has to be satisfied. This solution has to satisfy the paraxial wave equation. What is important is, see, remember, so very clearly you can see that if your this qz is this I lambda by pi w square, I get an exact Gaussian solution. Right? If I just put this, then I will exactly get what I wrote. I wrote something like I0 e to the minus r square by 2 omega square, right? If I write this, then I will get exactly that. But the important part is, this is actually telling me how this guy, so basically so very interestingly, let me write this properly. So I wrote something like, implies that I, if this I is something like I0 e to the minus r square by 2 omega square. I wrote this as a constant. It is not a constant. Okay, it is a function of z. Very important. This is something which is not very obvious. Okay, we are assuming that this spot size here, this spot size that we are talking about, this spot size here, is actually not constant as the beam moves in this way. And that dependency is what I'm trying to find out. I'm assuming that it is not constant. I will have to see, of course, at the end what I finally get. Is that actually a function of z, provided that this has to obey the paraxial wave equation? Is that a function of z now? I am not assuming that there is no z dependency. Okay, which is extremely important, and that will finally give us a lesson that you guys might have seen, that a Gaussian beam propagates like that, always like this. Okay, it is not like this is wrong. This does not go like this. A Gaussian beam propagates like this because omega, this waist, is not a constant. It changes when you are moving, when the beam basically moves. So in that way, it is not possible to have a perfectly collimated beam. However, what we shall see later is the bigger this sort of waist size, the smaller is the spread. The smaller the this waist size, you will see that it will spread much higher. Okay, so a collimated beam essentially is something which has a largish waist size, so that this spread is sort of slow. Whereas when you focus, when you have very small waist, it actually spreads out very fast. It's not a collimated beam, which is typically we don't call it a collimated beam. Okay, very good. Okay, so now we know that this has to satisfy our wave equation. So this has to satisfy my Helmholtz equation. Ah. 2ik del z E0 bar, but this has to be satisfied, right? Okay. So what we let us, so now you guys will work a bit. So can you just tell me first, find out, just tell me what this is. And then this is going to be a bit long. Tell me what this is. Please do that. Tell me. This first one is very simple. These two. फटाफट करके बोलो मुझे कितना आ रहा है. Both are functions of z, of course, qz and pz. So there will be, yeah, tell me.
Sir, what is that second factor? E to the power I. Is that
Pi
rho of
pz, pi p, q and p. Okay. There is a p, and so these are the Gaussian, famous Gaussian beam q and p factors of Gaussian beam. Famous. Maybe I should write like this. This one.
So you can take I A not as common.
Yes. Correct. No, अंदर का बोल.
Under that is k minus k by 2 into x square plus y square.
Wait. Sorry. Hey, by q square तो sorry. Minus क्या? K by
Minus k by 2 x square plus y square into x square plus y square
Q
into 1 by q square dq dz.
Very nice. दूसरा वाला
plus dp dz.
and ये क्या आएगा?
into IA.
I. Very nice. I into that whole thing. This is A. Okay,
A naught,
we
A
can
naught.
call this
Yes.
this whole thing is A naught and this whole thing, right? E to the blah 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 blah. Okay,
Yes.
and this one?
That one I didn't do.
बोलो करो ना, थोड़ा मैथ करो.
Sir, there will be a minus k square.
Hey, K squared? No. K square है क्या?
There is
Hey,
No, sir.
यहाँ पे K square
No,
नहीं
no.
है, right?
Plus, and it will be plus. Sorry, it will be plus, not minus. Plus k square.
No, sir.
Hey, not K square.
No, it is plus k, but not k squared, I think.
See, means there is already ik already there, and from the power ik1 again
ए
ik
स्क्वायर
will
क्यों
come.
होगा? आनंद, इट्स डेल ई डेल जेड, नो एक ही बार डिफरेंशियल हो रहा है, राइट? ये स्क्वायर क्यों होगा? ये फैक्टर जस्ट नीचे आ जाएगा और 1 by
जी
q square हो जाएगा. Why is it k square? This is one different. No, this one may have k square. This
okay
one
okay
will not have,
means
na?
sorry I was writing 2 ik del by del. Sorry that's
Ha,
mistake.
that if you write, then of course. No, I am writing just this
Sorry.
one.
Yeah, yeah.
When we add, then we will write. So basically, after this, we'll add 2ik and then do. This is just del E del Z.
Multiply, sir. Multiply 2
Ah,
ik.
sorry, multiply. Yes. No. So basically, we will do del square t0 plus 2 ik del E0 del Z. Then we will do. Na? See, this is very messy, yaar. I want you to do and tell me exactly. Hey, but guys, this one, if you do x squared, the same thing will. If you do x, so y uska exact hai, same hai. So it is symmetrical. If you know one, other one is the same.
It's a weird notation. Okay.
हुआ?
Sir, I think it is iota
Hmm. Hmm.
a times that whole thing.
That
e to the power.
यहाँ पे आयोटा है क्या?
हाँ, नहीं माइनस होगा, माइनस.
अरे ठीक से बोल यार, क्या माइनस?
अच्छा नहीं wait I haven't completed the calculation. Incomplete.
Ah,
So the del square t e0 is x plus y into I k by q
x
into
plus
eta.
y. ओए, del square दो बार है यार, x square x plus y है.
Okay, sorry. It's I think x square plus y square.
हाँ, correct. Yes. ए तुम लोग बहुत स्लो हो यार. उफ, I tell you many times. क्या है बोल?
X square plus y square into
माइनस या प्लस?
plus.
प्लस.
It should be same, right? So x square plus y
I
square.
don't-
Minus is outside. There's one
हाँ,
minus side
the
out.
wall ना, अरे minus is outside, right? So x square plus y square. Then
There is k square by q square,
very good.
and then
Q
a
square.
naught into the whole. That whole.
That is only this. Not only this.
Sir,
Not only
the
this.
plus 2ik by q,
Very good. Exactly.
whole multiplied by
Whole
a
multiply
times
that a
a
times
naught
that.
times.
So everybody, please, have you got this? थोड़ा करो यार, क्लास में और कुछ मत करो. Only time that we talk to each other. हाँ, ठीक है ना ये? रोहन ठीक है? This term has to be there, right? Because you are
Right.
basically हाँ ठीक है, right? Because 2x और ये आएगा, then वो दो x को करोगे कल ही वो आएगा. Okay, so then just add these very clearly. If I add, तो तेरा आता है, so I can just so this one is same. So
2
basically if I
ik er by q.
हाँ, so 2ik जब multiply करेगा तो ये k square ये same आ
Final
जाएगा.
expression, sir. Final expression.
हाँ अच्छा बोल.
2 ik er.
Oh, I am no. Wait. I want you to write it like this. Tell me कि I am taking k square by plus x square by k square by q square. इसका अंदर क्या है बोल? और I am saying plus 2k. इसका अंदर क्या है बोल? a0 that thing. ऐसा बोल.
dq over dz minus 1
This one.
plus 2ik er by q.
अरे इसमें क्या है? अरे अंदर कॉमन लेके बोलना क्या है? No, where is the dpdz gone? अरे let me write it since everybody is so slow. Is this correct? Clear, right? ये तो आएगा.
Yeah, it is correct.
Correct ना?
Yes.
Okay. Nice. Okay. So very clearly, we basically these cannot be zero. So this one and this one have to be zero because the right hand side is zero. This is zero. So essentially that means I have two conditions. dq dz is 1 and I have dp dz is I by qz. So देखो both of them are clearly functions of z. Very clear. So very nicely this tells you that even if you assume that you do not know if there is a z dependence, the paraxial wave equation sort of it ensures that there is indeed some kind of a z dependence here. So that means I can just write this is very simple, that this implies this q is some z plus some q0 constant, and your this one tells you that this dp is some acha. So I will a q I can put here, right? This qz I'm putting here. So basically this becomes I dz by z plus q naught, right? Acha, abhi I'm going to obviously put some kind of a boundary condition. So okay, so this one implies that your pz is nothing but I log of z plus u0 plus some log of c constant. Acha, here we will make a sort of thing, that assumption that a is equal to 0, where the origin of coordinates I'm taking p to be arbitrarily 0, which means that c is nothing but your minus of q0, right? So q0 matlab then basically it is the value of q at z equal to 0. Okay, so this is nice. So I'm actually from here I'm putting this condition like that. So this tells you that z equal to 0 means what my value is. That is the value of q0, which tells you that your p is I log of z plus q0 by q0. So I have got my two dependencies.
So what happened to the iota while calculating the boundary condition?
Where here है ना कौन सा?
No. At z equal to 0, p is 0. So 0 equal to I ln of q0 plus ln c.
Yeah. No, I am taking this to be a constant. At z equal to 0, then this is.
No, I mean I'm getting
No,
ln.
यहाँ पे भी I है ना?
So there should be one more I.
Yeah, sorry, of course. Sorry, obviously.
Sir, physically, what
there's an
does
I.
this boundary condition mean?
So basically, it is saying that as I am starting my origin of coordinates, so we will see. So let us just see. Our target for today will be to find out this omega z. So remember, I wrote this as this thing, na? This omega z is the waist size. So we are going to say that somehow this q relates with waist size. So essentially, this will tell you that the beam finally evolves like something like this. ऐसा जाता है. So this is my z equal to 0, and it will just grow as you go out. Okay, the minimum size of the beam is what we define as my origin of coordinates. So it is only going to diverge after that. The transverse extent of the beam is basically going to increase. Okay, that is what we are going to come later. At the moment, that is not clear, but as we proceed, you will see that is what is going to happen. Okay, So this is my two things now, and let us just keep on doing this. Okay. So Gaussian beam.
Sir,
Okay.
I did
Hmm.
not understand in the beginning why we needed e to the power I p z exactly. P of z.
See,
Like,
those are two
if
phase
assume,
factors that we are seeing. So
like I
basically,
understood qz, like
uh,
we cannot assume
hmm.
that the
No.
waste
So
length cannot.
basically, see when we when we finally do it, you're going to see that the amplitude. So I remember I am looking at
E to the power I p of z is some kind of a phase term only, right?
phase, yeah, right. So basically there is another yeah, I mean this is a bit vague. So finally when we do it, we will see that it comes as an amplitude. Okay, when there is an extra thing that comes as an amplitude, the envelope comes. So yeah, I mean why you need that, uh it's a I don't really have a great answer for that, actually, because so you will see that it comes, there is a nice thing which, so I don't know, maybe when we look at the paraxial wave equation, no, so maybe one can say that, the wastes, yeah, okay, so one can probably think of that, one is giving you something about the beam waste, which is the transverse extent of the beam. Other one is the dynamical phase. Okay, something like as you go, you can think, but there is no time as well. Uh, when we go ahead, we can see that why you write that is
Sir,
not very
also
clear, actually.
here
The way
also
they treat. Bolo?
qz is that the wavelength over here?
QZ we will find. No, that's what. Let us proceed. So
Okay.
why we actually, that is a, I
So
don't, yeah.
even
Let me
that
just
term is in
think
e
of
to the
it.
power I k. So
Hmm.
I don't know. It also everything seems like a phase term only. Is that
Yeah, it's all a phase term. Completely agreed. It is all a phase term, but you will see that finally the things will come in such a way that one will give you waste and the other gives you some kind of
okay,
amplitude
sir?
modulation. But I completely agree with you that this is a bit arbitrary. See, if you find a better treatment, you can let me know. But uh, so okay, one thing we can say is that you can, because we are intuitively knowing that there is going to be a Gaussian, we are basically going to keep something which is going to look at the Gaussian beam size. Okay, Gaussian, I mean the sense, waste, how big the spot becomes, that is one dependency. Certainly how that changes with Z, that is important. Other thing that we also have to keep in mind is, because it is a sort of an x square plus y square kind of thing, which is, so it is kind of representative of a circle, right? So that means there's going to be a radius of curvature. Okay, so the radius of curvature, that also is going to be a function of Z. Okay, so that, now
Sir, what
why
is of curvature exactly?
the radius of curvature? So in the sense that, since we are, so there are two things we consider. So basically we know that Q is complex. Okay, and it has two properties, right? Now Q also has, so okay, no, I should not write Q. So basically the a Gaussian beam, because it has it will have a spot size, and because it has this x square plus y square kind of a dependence on the top, what we are saying is that that also has a curvature. It's like a circle, so it has a radius of curvature. Okay, so what is done typically is that you say that this is complex, so you write something like this. This is something that you write. Now, this is But this is so basically I'm just breaking this into real part and imaginary part. But finally we say that this is the beam curvature, because what we will finally see is that it will resemble very much a spherical wave. Okay, so again you can say that by intuition we think. So okay, let me speak this. Okay, maybe that this is where you can sort of think of. So because there is a kind of radius of curvature, we kind of think that, see, you have this E0, sorry, this we have this A0 something, right? Something like that. Now, because there's a radius of curvature and the beam is kind of diverging or something, I have again an intuition that this also will be modified. So basically the modification of this, that is kind of embedded in the P factor. So the waist is embedded in the Q factor, and the amplitude modulation or whatever, that is embedded in the P, in the P factor. Okay, suppose I say that. Now I took them as phase, I know, because I essentially took them as complex quantities. Okay, I took them as complex quantities, but I'm saying that there will be, because okay, so because I know that, you know, a spherical wave is something which is not like a plane wave, right? It does not have infinite extent, right? So I'm saying that my transverse intensity profile, that will have some aspect of a spherical wave, and that, and of course because it is limited at the edges, because it's sort of cut at the edges, it also looks like a, it, I mean the natural thing to, you know, the function which sort of satisfies this requirement is that of a Gaussian.
And sir,
Okay,
that exponential term is not a phase term, sir. Because when it will be a phase term, if Q is a perfectly real, but
yeah,
your
that is
Q
correct,
is
actually
not
that is
perfectly
correct,
real.
yes, that is very correct, that is very correct. So remember, both P and Q are complex.
You are, yes. So
Yes.
Both
that
P
is
and Q
not,
are complex. So
so
I'm
that
not
is
saying
not
that
a
these are
phase
correct.
term.
Absolutely right. So these are not completely phase terms. Okay.
So
So
that
I, my
will
only, yes, correct.
actually, yeah, that will help the intensity to be Gaussian.
Now, but at the same time, Bishwajit, we are kind of starting with the intuition that this is a Gaussian, right? That is for sure. Because otherwise, you choosing that x square plus y square by something, you know that
Ah,
when Q is,
that is coming from, sir,
that is
actually
coming
spherical solution.
from spherical, say, yeah, correct. So,
That is coming from spherical solution. But
right.
then you are finding that those components are not are completely phase term. Then
Yes.
if it is a phase term, then it going to the spherical solution again.
Right. Spherical
But
wave
it is
thing.
not
But
a,
as I said, my closest answer is that you will want some kind of dependency of the A0 and some kind of dependency of the that exponential stuff also, right? So
and
what we will
they
see,
will just,
yeah,
you
they will
already
just,
wrote the thing that one
right,
cube,
it is
one
already
by
there.
three.
You can already see that it is going to work. So once I write this, this we kind of term as the radius of curvature, and this is the spot size. And this is again, intuitively, you can see that this is very close to what we need for, you know, for when this is a constant, then we exactly get back the Gaussian term. And you can also see that this is, when you put it back, you get something that is extremely close to Gaussian, except that the W is not a constant, it's a function of Z. Okay. And also you can see that when so when you see that when R tends to infinity, then clearly your 1 by Q is I lambda by pi omega square Z, which is basically again becoming, you know, this is when you put this expression on our solution on the test, I mean the nature of the solution we wrote, this is going to come to exactly Gaussian. Okay. So this thing basically comes because there is a spherical wave also, you know, that part we are not throwing out, because that indeed has the problem that this is not a solution for the beam like structure, is that this is not unidirectional. But then the amplitude still definitely changes as you, I mean, It is also, it's not, it does not have infinite extent. That is important. Okay. Now we'll stop here. I mean, just one thing I will just write. So basically, if we just consider your e to the I k x square plus y square by 2 qz e to the I pz, you basically have uh, you basically this first thing what you will have is, so just the first part I considered, this one what I consider, then I have is e to the I k x square plus y square into 1 by rz plus I lambda by pi omega square z, right? And uh, this is, and this, so obviously this is essentially I to the I k x square plus y square by rz into e to the minus x square plus y square by just your omega z square, right? And your e to the I pz, that is nothing but e to the minus ln q0 plus z by q0, which is just q0 plus I sorry q0 by z plus q0. Okay. So I think, yeah, yeah, maybe we will stop here today. So maybe next class I will continue.
Sir, but I am confused at one point. We calculated q of z as z plus q naught,
Yes.
and then we are
What?
writing.
No. That is different. I am saying that this is completely different because Q is complex. I am saying that I can write it as some kind of a real part and an imaginary part. Okay, where this imaginary part is abiding by my requirement that this has to be a Gaussian, and this my intuition is that there has to be a radius of curvature and there has to be a waist size. So this is a separate thing that I am saying, that if, since this is complex, I can break down, say, because q equal to q0 plus z gives you nothing, right? Whether it's real complex, it gives you nothing. It's just two parameters. q0 is not a physical parameter on which you can intuit anything at all, right? It is just
No,
whether it's real complex, nothing you have. No.
but then why did we calculate it? I mean, now we
No,
have some
that is
something
crucial.
new.
Arey, यहाँ पे we'll put no. See, because we calculated it because we had this now. From there we got this na. PZ ka we got this, right?
So
Arey,
now we are using the definition of q which we had derived earlier, but
yes.
the
But
q
then this is the physical reality, the physical meaning of Q we are essentially attributing from here. Okay, we are saying that there is a radius of curvature. I mean, there is a real part and there is an imaginary part. Okay.
no. The
So,
part where I'm confused is you are using two different definition of q in one. Uh,
yeah, in the sense that one is a,
No, the
so
relations are different, right?
yes, they are
Q
very
equals
different
to
in the
Q0
sense,
plus
yeah.
Z
So
is dependence on Z, not on
yes,
R or the omega.
yes, and very
So there must be
crucially,
two different things.
and no, and very crucially again, Rohan, is that one is a consequence of my paraxial wave equation. That necessitates that I have this to come, q equal to q0 plus z, how q changes with z. Now I am saying that if I have a beam which is going to look like a Gaussian and a sort of the q parameter, so think of the q parameter. So the q parameter, q parameter we have said is complex. It is representative of the Gaussian beam. Okay, and we are saying that it is complex. Don't confuse this with what we had as a requirement to satisfy the paraxial wave equation. That was just a mathematical progression where we said that if this has to solve, if it has to obey the paraxial wave equation, q has to be that. Now remember, I took a solution of the nature of e to the sort of iq, e to the ip, where both q and p are complex. Okay, now I'm saying that q is a beam parameter. So essentially, let me write here. What I'm saying here is Q is a beam parameter and Q is complex. That is also fine. So that I'm saying that I'm writing the real part and the complex part like this. And the reason that I do that is that when I say that I knew that when Q was equal to this part, I kind of get exactly the Gaussian solution back. Okay. But I'm saying that there also is a real part of Q, which is I represent as this. And when this term becomes infinite, which is essentially when it becomes a plane wave, I mean, that we'll come to later again. When this is well, rather RZ is infinity, R is infinity, then this is exactly that. And you know that this satisfies the condition of my intensity distribution of the field being that of a Gaussian. Okay. So those are two different approaches. One is just the requirement for solution of the paraxial wave equation. This is my intuition of this being a Gaussian like nature of this beam being, where Q is the complex beam parameter. It has a real part, it has a complex part. The beam has a radius of curvature because it's like a spherical Gaussian. I mean, because spherical waves are actually, because I have anyway taken that, a Gaussian cross section, if you take, it has a resemblance to the spherical wave. So I'm saying that there's a radius of curvature, and I'm saying that the spot size or the extent of the beam, that is given by this beam parameter omega z, which is essentially the physical meaning is the intensity at 1 by E square of the spot size.
Sir, just one question. This Gaussian beam like follows the paraxial wave equation, right?
Yes, absolutely.
So then we could have just used this definition of Q and have put in the paraxial wave equation to get a relation for Q and P.
Yeah, but that is no. But then you're not getting any beam parameters from there, no. See, what is important is I'm saying that there is a finite. So, see, basically, if you think of it, no, okay, let us try to understand again. So, suppose you have when the beam evolves, right? So it can either evolve like so. Like say this, or it can evolve like say this, right? So there are two things changing, right? One is this size, and one is this curvature. That is very crucial. So how do you represent that curvature? Because that does not come from the paraxial wave equation at all. Right now, basically,
So what do you mean it doesn't come from the paraxial wave equation?
in the sense that if I do not get this, I mean, sort of in this, it doesn't come, what I'm getting is just some, so from the paraxial wave equation, what we got was that Q equal to some Q0 plus Z. So what is the meaning of Q0, right? That I'm not getting from there in any way, right? I am physically sort of ascribing that the Gaussian beam essentially has a curvature, because remember that when we take a cross section of any beam, that looks like a circle, right? So that has a curvature, right? So that needs to have a curvature, that needs to have a diameter, horrible diameter. So the diameter is, let me just put it properly. If you just think of this, it's like that, and there is a diameter and there is a curvature because it's a circle, right? This is the curvature. So that this cross section, when I actually, this is the longitudinal, this is the Z, and this is the transverse. When I take any cuts here, it looks like a Z, but when we have a succession of circles, then this is essentially the curvature, right? So this I am saying is not manifested from here. So any beam, think of it, any beam, if I take a cross section, it is a circle, it's a sphere, right? It's a circle, not sphere, circle. So therefore, there are two parameters of a circle. There's a radius of curvature, there's a curvature, which needs as a radius of curvature, and there is a spot size. So those I am saying, so this is a very clever way of sort of, getting the requirement from the paraxial wave equation, and then from our, experiences with beams, also relating the physical properties required of beams with the requirement for the paraxial wave equation. Those two we are sort of integrating or marrying. You got this? So basically I'm saying that if you take any beam, if you take a cross section, it is a circle. If you take a cross circle, that there is a spherical, there is a radius of curvature. right? I mean, a circle like this and a circle like this, there is a huge difference, right? There's no circle, whatever, you can pardon my drawing, but there's a
Means,
big difference,
sir,
right? So that is where I'm integrating this
I
part.
get the point, but why
Yeah.
haven't we? I'm still confused that why didn't we use this definition of radius of curvature and spot size when we said that this is the solution of partial wave equation?
No,
Because we
in
are
the sense,
interested
it's
in
the
Gaussian
same
wave.
thing, right? Whenever I could have written this there itself, I
Right.
could have written this part there itself. Yeah, that is okay. I mean, you can, but you see, for handling this huge terms in that, come on, man, this is much more simpler. I mean, you can of course write it there and keep on differentiating and going crazy, right? If you had a one thing to different del q del z, इधर पे तुमको तीन आ जाता, right?
Okay. Okay.
So
Just one
this is
question.
just for convenience.
Can I equate this 1 upon r plus I lambda by pi omega square equal to 1 upon z plus z naught?
Huh. That's what we're going to do. Arey, give me. I'm stopping today. No, tomorrow we are
Okay.
exactly going to pick it up from here.
Okay.
We are exactly going to pick it up from here. Okay. Tomorrow we are going to start from this, and we are going to yeah. I mean, just finish this part. This is very nice. I mean, the thing is beautiful, and what is wonderful is we are actually going to see that the evolution of the Gaussian beam is identical to diffraction through a circular aperture. It is absolutely identical. It is the same. Okay, that we are going to do, but once we finish the Gaussian beam and the resonator characteristics, then we are going to do diffraction, and then diffraction through a circular aperture is what we're going to look at. This is exactly the same as the Gaussian beam. Okay, so yeah, so
Sir,
today we'll stop. Huh? Bolo.
sir, the thing is, uh, based on experience, you can define your Q to be this. I don't have any problem as such.
Yes, yes,
But
yes.
will dq dz be equals to 1 in this case?
It has to be. We are going to follow that. Yeah. तुम थोड़ा धैर्य रखो
But
ना. Tomorrow we are going to do exactly that. We
the
are
thing
basically
is,
going to take q0 plus z, and then we are going to exactly completely obey those and go ahead and prove. Okay, so basically that's what we are going to exactly do. That is one little another assumption we
I
have to
didn't get
take.
the doubt. What was the doubt exactly?
So
my doubt
Hitesh
was
is saying
you
that where
can
am I obeying that dq dz equal that q equal to q0 plus z? Where are we obeying that? We are not following that at
from
all.
the Helmholtz equation we got that condition right for
Where are we
this
using that? अरे
dz
भाई
has
अभी
1.
पिक्चर अभी बाकी है, पिक्चर अभी बाकी है,
I
पिक्चर
think
खत्म
like
नहीं हुआ.
q is equals to q naught plus z. If you just take
हाँ
1
वही
by q,
वही
I think you can
exactly.
get it, na? I
Right,
think you
right,
can equate
exactly.
both the
That
sides.
No, therefore, what we are going
there
to do basically at the end, at later on, is that when we said that r equal to 0 is where q0 is there, right? So then we are going to assume that r part is infinity. Okay, so that 1 by q becomes basically q0. This part is q0. So I'm going to say that when r equal to with q, this z equal to 0 is 0, this is going to blow out. I'm only going to keep this part. That is basically my q0. That's what we saw here, right? So this is what we're going to define as my origin of coordinates. So when I am, so basically when at the focus of the Gaussian beam, the radius of curvature is actually infinite. It is a plane wave. It is a perfect plane wave. Okay. So essentially we are going to use that. I mean, we are going to write that q equal to q0 plus z, but that q0 I'm going to say is where r is infinity at z equal to 0. But before now we have seen that q equal to 0 is what I say as q0, right? So I'm also going to say q equal to 0 is that point where the radius of curvature is infinite and it is only just this. But we are going to absolutely use what we did, those two things that we had. But anyway, I'm going to start from this step tomorrow. Okay. And then we are going to do the other part and find out things. Okay. Okay. Tell me, और कुछ है to discuss? Yeah, guys, nothing, right? So let me stop the recording.